Guys, let's go. We got parallel and perpendicular lines. This is right after the unit test. Everything went good on that. Myself, I got a good grade. I got 100 on it. Just using based off the notes, everything like that. So our next content's going to get into is our next unit is angles and lines. So now we're going to have to start getting into that. Well, let's go ahead and get started. I'm going to share my screen with y'all. Here we go. There it is. And what I got here is I got my Dochub. Remember, it's just a Google search Dochub. I'm going to go ahead and grab my guided notes. So I got to download these since I haven't done it yet. I'm putting them inside of my guided notes in my desktop, my guided notes. I'm going to save them right in here. This is parallel and perpendicular lines. Go ahead and save that. Okay. Close this out. I'm gonna go ahead and start a new one on my Dochub. And let's see, I saved it into my guided notes, perpendicular lines. Oh, here we go. While that's loading, let's go ahead and click on the warm-up. Get ready to go. Change my size of my font. I'm going to go ahead and go with maybe the 14.
Have you ever noticed in architecture, such as the architecture of bridges, that you can find a lot of parallel or even perpendicular lines? Architects use a lot of these types of lines because they have a nice visual appeal, but also good engineering reasons. In this lesson, we'll be taking a close look at the relationships between lines and line segments when we ask the question, what special relationships exist between two lines or a line segment and a line?
I wish I typed faster. I'm not a very good typer, but that's all right. It doesn't really matter. Okay, so let's go ahead and get on to the next one.
Our goals for this lesson are to solve problems involving relationships between lines, and then we'll see how to apply transformations to construct a parallel line. We'll also solve problems involving distance from a point on a perpendicular bisector. And lastly, we'll see how to identify parallel, perpendicular, and skew lines in three-dimensional figures. As we do this, we have some key words and phrases to know. And I suggest you pause the video if you need to and write down their definitions. You can find them in your e-glossary. These phrases are parallel lines, perpendicular bisector, perpendicular lines, and skew lines. Let's start by remembering what the definition of parallel and perpendicular lines is. For parallel lines, they are coplanar lines that do not intersect. Remember that the word coplanar, well, that means that the lines need to be in the same plane. And also remember that a plane in Euclidean geometry is a two-dimensional object that extends infinitely in both of its dimensions, and it has absolutely no height to it. So we see some parallel lines here. They must be in the same plane, and we indicate that they're parallel with those arrows right there. Perpendicular lines are coplanar lines that intersect to form a right or a 90-degree angle. Those mean the same thing, right, and 90 degrees. And on this diagram here, I can see that I have a right angle because of that right angle marking. And in fact, I know that these are all right angles because, well, this right there is a 180-degree angle.
Straight line.
So these adjacent angles must sum up to 180 degrees, and therefore they're right angles. And the same thing can be said about all the other angles in that diagram. Next, to make some conjectures about the relationships between line segments.
Okay, so I'm just going off of these, knowing what they are. He said that the coplanar are lines that are on the same plane. A plane in Euclidean geometry is a two-dimensional object that extends indefinitely. Because all lines, they go indefinitely. They just go on as far as, and they have no height or its dimensions. So he kind of pointed that out a little bit ago. He might even go back over it.
Lengths of the line segments and locations of the segments in a right triangle.
Okay. Make a conjecture about the diagram below. Is AC greater than, less than, or equal to BC? AC, BC. It my opinion, that's going to be longer because the shortest point between any 2 points is a straight line. Well, this one, if I was to extend it down here, I'm thinking that it's going to go down here. So I think it is greater than. Okay, and it's because it's a further distance. Let's see if that's correct. Okay, AC is greater than BC because the segment AC is the hypotenuse of a right triangle ABC, and the hypotenuse is the longest side of a right triangle. Okay, so what did I apply on my? I put that it is a greater distance, so I definitely did that. I didn't say the word hypotenuse or reference the right triangle because I wasn't thinking along that line. These are some great points though to that. You got to make sure that you understand that. So now my thinking is that I have to understand a little bit better of what I'm being expected to ask and answer, and how my thinking has to go from here. All right, so in this one, let's see the shortest distance theorem. Slide 2. Let's go ahead and see if this is this right here. So the shortest distance. Okay. The shortest distance from a given line to a point not on the line is the length of the segment perpendicular to the line through the point. Okay, so let's use our drawing tools to go ahead and create some lines here. So I don't know. This isn't the same as this. So what I'm gonna do is I'm gonna go ahead and I'm gonna pull up the next one because I know the answers to those, but I don't think that that's what it's asking us right now. I don't think we've gotten to that point yet. So why did it not give me this? Let me go back in and click it and make sure that I went all the way through it.
Lengths of the line segments and locations of the segments.
Okay, so now I'm done.
In this lesson, you will learn about the relationships between points and lines, as well as some theorems involving them, and parallel and perpendicular lines.
Mm-hmm. Okay, so remember, you got to make sure you click on all the buttons. Instruction. Let's go ahead and keep on going with the instruction now.
In this lesson, we're asking what special relationship exists between two lines or a line segment and a line.
Come back up here because it's probably going to tell us something.
We could have that the lines are parallel, or we could have that the lines are perpendicular. In the next part of this lesson, we're going to take a look at the relationship that exists between the distance that you can measure between a line and a point that is not on the line.
Let's see. So lines that are non-coplanar and that do not exist are skew lines. Okay, lines that intersect to form a right angle or 90-degree angles are perpendicular lines. A line, ray, or segment that intersects a segment and it's perpendicular to the segment is its midpoint. Well, that's a perpendicular bisector. Okay, so that word we should already have known that because we've seen perpendicular bisectors before. So we should already know those ones. So let's go ahead and move on to the next part.
The shortest distance theorem states that the shortest distance from a given line to a point that's not on the line is the length of the segment that's perpendicular to the line through the point. Mm-hmm. So let's see what we mean with this example down here. I have line AB, and I also have a point C that's not on the line. Well, this theorem tells me that the segment that's perpendicular to AB and which intersects with C, so I have that segment right there, well, its length, we can call it CD, is the shortest distance between C and the line AB.
Okay. So now let's go ahead and label that as D. Point D. Okay.
Let's prove the shortest distance theorem. We are given a point here, C, and it's not on the line that we're given, which is line AB. And what we need to prove is that the shortest distance from C to AB is the length of the segment that's perpendicular to AB and goes through C. Let's start actually by drawing a perpendicular line segment from C to the line.
Okay, so on your guided notes, it's already done for you.
Now, the reason we're able to draw such a line is by using some reasoning with the unique line postulate. We need to show that it's the shortest such line segment, the shortest line segment that goes from C to the line. Well, in order to do that, we're actually going to take another line segment that goes from C to the line. And I can draw it like this, and we'll call that intersection point E. What we need to know is that the length of CD is shorter than the length of CE. Well, I was able to draw that line segment CE by the unique line postulate again. And I want you to notice that triangle ECD is actually a right triangle. And that's by the definition of a right triangle. And furthermore, CE is the hypotenuse of that right triangle. And that's because it's opposite the right angle, which means that by the definition of the hypotenuse, we know that this is the case. We know something about the hypotenuse of a triangle. In fact, we know that it is the longest side of the triangle. And so that means that CE is the longest side of this triangle. And specifically that the length of CD is strictly less than the length of CE. And we know this by the definition of the hypotenuse. But I want you to notice now that in step 5, we've actually gotten what we needed. We started with any other line segment than CE. And we showed that we can always make this right triangle. And when we do that, we always end up with the hypotenuse being longer than CD. So this actually proves that the shortest distance from C to line AB is the lines or the length of the line segment CD. This is exactly what we concluded in step 5. So this proves the shortest distance theorem for us.
Okay, so I was just listening to that, so now I'm going to go ahead and fill in my notes. The shortest distance from C to AB is CD, which is line CD. Okay, the definition, unique. So this is the unique line postulate. That's where this is at. The unique line postulate is also, these are just basically these lines here is what he's talking about. The definition of a right triangle, the definition of a hypotenuse, make sure I spelled it right, and that's a conclusion from step 5. Okay. I'm gonna pause this for just a second. All right, I'm back. Sorry about that. Okay, so let's move on. So on these ones, I really recommend you sitting here listening to this guy and seeing what he got, gather the information, follow along on here, then come back and fill in these parts right here, because now we're on to slide 4.
Use the tool to construct a line parallel to line N through P.
Okay, so construct a line that is parallel to the given line. Why in the world is this not letting me move? See, that's what I was trying to do. Why is it not letting me get a... Oh, God. Okay, so I was supposed to move the line. Did you guys see what happened there? There was a line down here. It said construct a line through the points. I thought I was going to be using this. So move the compass center to Q and draw an arc that intersects both lines to the right of Q. Okay, so... Okay, so there we go. Now this is what's going to draw it. This will open itself up now. Okay. Without changing the compass radius, move the compass to the center of P. And draw another arc that intersects both lines. Okay, that was correct. Move the compass back. Move the compass center back to A. Okay, and adjust the radius so the compass of the edge is at B. Move the compass to center C. And draw an arc that intersects through the other arc. So just like that right there. Construct a line through P and D. Okay. Here we go. Okay, so the first thing you gotta do is go to Q, P. Okay, put this right in the center of here. Draw through both. Drag it to P. Draw through both. Move this back to A. And right there. Now go ahead and put this on C. Draw right there. Move this guy out the way. Go ahead and put this through P. This through D.
Congruent corresponding angles are used to construct parallel lines.
All right. Okay, so this is just doing the same thing. Could quickly do it, get a little bit extra practice in on it, just to make sure that you understand what's really going on here. Pretty easy. Pretty easy, guys.
Congruent corresponding angles are used to construct parallel lines. You've seen how to construct a line that's parallel to a given line and that crosses through a point that's not on the given line. Well, actually, we can say a little bit more than that with the parallel postulate. Parallel postulate says that given a line and a point not on that line, there exists exactly one line in the same plane that passes through the given point and is parallel to the given line. So in this example right here, I see I have a given line, and if I try to draw it carefully, I can draw a line through that point that is parallel to the line that we're given. Now, the parallel postulate says that there's exactly one such line in the same plane. And I'd like you to imagine trying to draw a slightly different line. I can see that any other slightly different line, it cannot be parallel because it's going to have to eventually intersect my given line. What can we say, however, about lines that are not in the same plane? Well, in that case, we can talk about skew lines. Skew lines are lines that are non-coplanar, don't lie in the same plane, and also that do not intersect. So in this diagram here, we're given that planes R and W are parallel. Remember that we can think of planes as consisting of infinitely many lines. So let's just take two of them right here. We have lines DE and line FG. And if I take a look there, I can see that those lines, they don't ever intersect, but they're also not in the same plane, which means actually that these are an example of skew lines. We can write DE and FG are skew, or skew lines. I'd like you to note that perpendicular lines are not skew lines because remember, they're in the same plane. By the same token, actually, parallel lines are not skew lines because they're in the same plane. So let's see if we can identify some different examples of parallel and perpendicular and skew lines. Here we're given a three-dimensional diagram, and it has two planes, planes A and B, and we've also taken some lines in here, and we're asked to identify any parallel, perpendicular, or skew lines. But when I look at this diagram, I see that lines P and M are marked as parallel. So I can say, okay, P and M are parallel, but I can't say that about any other line pairs because there are no such markings in the diagram. Remember that we can't assume too much from a diagram like this. How about perpendicular lines? Well, I see that lines L and N have a perpendicular line marking between them, so I can write them as perpendicular. However, there are no other pairs of perpendicular lines on this diagram. Next, we need to identify the skew lines. That means we're looking for lines that are in different planes, non-coplanar, and lines also that don't intersect. Well, when I look at this diagram, I see that lines P and L, those are in different planes and they don't intersect. And also lines, let's see here, L and M, that's another line pair. And these guys are in different planes and they don't intersect. And that actually takes care of all of the skew lines in this diagram.
Okay, so while I was listening, I wasn't sure how far he was going to go, but the parallel postulate, that given a line and a point not on that line, there exists exactly one line in the same place that it passes through the given point and is parallel to the given line. Okay, so if we're going to draw this just like he did, okay, what he did was he just drew straight through like that. Okay, if that one right there, it's not the greatest, but again, you just refer back to what he said about it. If it goes down too much at some point, even if it's way down the line over here, it has to be parallel to that. So let's see, skew lines are lines that are non-coplanar and do not intersect. Okay, in this diagram's plane R and W. So what that basically means is if you're looking at it on there, but this is what it's talking about. These are planes, and see they just stay like they're parallel to each other. So that's kind of what you're looking at. You're not looking at two pieces that are side by side like this that are flat. You're actually looking at them like this. They're on top of each other. They're parallel to each other. So if you can visualize that, that's exactly what it is. Or two pieces of paper, that one paper's here, one paper's on the bottom, and then when you fold them over, they kind of just kind of rotate around each other. Okay. DE and FG are parallel lines. Wait, I'm sorry. They're skewed lines. I don't know why I said that. Skew lines because they're not parallel to each other. The planes are parallel. The skew lines are just lines in between. They can go in any direction. They do not intersect. They have nothing to do with each other. Perpendicular lines are not skewed lines because they are in the same plane. Parallel lines, let me move that up. Parallel lines are not skew lines because they're in the same plane. Okay, so the planes are parallel, but the lines are not. Okay, we got those ones filled out, so now we're right here onto this part. Let's go ahead and get up next.
Use the diagram to answer the question.
Okay, so what I see right here is that these two are teed off on each other. These two are teed off on each other, so they're flat. If you could visualize that, this is what you're looking at. It kind of looks like you're looking at it kind of like this, where they're actually connected into each other, kind of like that. But they all go through. Okay, which are the lines that will intersect? It's telling you which ones are intersecting. It intersects right at the fold, right at the midpoint, and you're looking at line B and line D. What are lines that will intersect? Line B is on M, and line A. So it's going to be these two because C is on this plane of plane N. So it's actually A and B. Which lines are perpendicular lines? Well, now the perpendicular lines are going to be, now it's line D and line B. Which are skew lines? C's a skew line because they won't ever go. A's a skew line because those ones won't ever meet up. I'm going to go A and C on that one. Let's see if we're correct.
Now let's look at a theorem involving a line that is the perpendicular bisector of a segment. In this lesson, we're asking what special relationships exist between two lines or a line segment and a line. And so far, you have constructed parallel lines, you have investigated some properties of parallel and perpendicular lines, and you've even investigated these types of lines in 3 dimensions. Next, what we're going to do is we're going to take a look at what happens when a line intersects a line segment. And specifically, we're going to take a look at what happens when a line bisects a line segment, just like I've drawn right here. The perpendicular bisector theorem tells us about the distance between points along a perpendicular bisector of a line segment and the line segment's endpoints, shown right here. In particular, we already know that a perpendicular bisector must intersect a line segment at the line segment's midpoint, which means that actually that point, which is on the perpendicular bisector, is equidistant from the 2 endpoints of a line segment. Well, the perpendicular bisector theorem actually tells us that all the points on the perpendicular bisector of a segment are equidistant from the endpoints. So for example, if I were to take a point S, then the perpendicular bisector theorem tells me that the distance between Q and S is equal to the distance between R and S, which means that these line segments right here are congruent. I can also take a point that is below my line segment. I could take a point down here, call it E. Well, the perpendicular bisector theorem tells me that the same thing, actually, that the distance between R and E is equal to the distance between Q and E, which once again, I can draw line segments like so, and conclude by the definition of line segment congruence that they are congruent. Let's go ahead and prove this theorem. Here we are given that P is a point on the perpendicular bisector L of line segment MN. And we need to prove that the distance between P and M is equal to the distance between P and M. Well, we can start by using the unique line postulate. We know that there is exactly one segment between points P and M. Now, after I've drawn that segment, what I can do is I can reflect it across line L. It'll look like this when I'm done. Now, when I do that, then by the very definition of reflection, I know that P is in the image. It is actually just the image itself because it's on the line of reflection. And furthermore, N is the image of M. Furthermore, I know that reflection preserves lengths, and therefore these line segments are congruent. And in fact, we get from this fact that the distance between P and M is equal to the distance between P and N. And that's exactly what we needed. We needed to know that any point along the line L is equidistant from the line's two endpoints.
Okay, so this is just putting some prior knowledge back in, talking about some reflection and stuff like that. So you guys kind of, from the last chapter, you guys will see what, like, you guys should understand what reflection means. That should automatically just tell you it's a mirror image.
Complete the statements in the proof of the perpendicular bisector theorem.
Use the drop-down menus, complete the proof. By the unique line posture, you could draw only one segment CD using the definition of perpendicular bisector reflect BC over L. By definition of reflection, the image itself is A, and A is the image of B. Since reflection is preserved, this preserves the length.
The segment that is drawn is the same one that is reflected.
Okay, so by the unique line postulate,
Now that you have proven the perpendicular bisector theorem, let's examine some of its applications. Let's use the perpendicular bisector theorem to solve a problem. Here we're given a diagram, and it has a line segment AB and also a line L. And what we're asked to do is find the length of line segment AC. If we look closely at this diagram, I can see that the distance between A and D is equal to the distance between B and D because those line segments are marked as congruent. Furthermore, I see a right angle marking. So this tells me that the line L is a perpendicular bisector of line segment AB. And furthermore, since point C is a point on line L, I know that it must be equidistant.
How's it going? What you doing? Good.
From the endpoints of line segment AB. So that tells me actually that the length of AC is equal to the length of BC. And we can use that fact along with these expressions to write an equation that we can use to solve for X. After we've solved for X, we can substitute it into one of these two expressions and we'll get the length of AC. So here what I'll need to do first off is combine length terms.
So
and I'll start by subtracting 3x from both sides, and that gives me that x minus 5 is equal to just 2. Now I can add 5 to both sides, and I get that x is equal
to 7. What you guys doing?
At this point, what I can do is substitute 7 in for my expression for AC. And when I do that, I learned that AC is equal to 4 times 7 minus 5.
28
minus 5, which equals 23. So I know now that AC must be 23 units. And furthermore, since AC has the same length as BC, I know that BC must also be 23 units. Find the length of segment SR.
SR. So let's go ahead and annotate this. So this is 2x plus 8 equals 8x minus 4. Okay, so when you set them equal to each other, I don't want to bring over this a because that creates a negative over here. So I'm going to bring this way. So this is going to be minus 2. So minus 2x minus 2x. Over here, we're left with 6x minus 4. Okay, so now I got to add the 4 over here to get it out of here. So that cancels these two. Those two got canceled a second ago, so now this is plus 4. So this is 8 plus 4 is equals 12, and that's 6x. So this is 12 equals 6x, divide by 6, divide by 6, x equals 2. Okay, so now we got to put this 2 back into this one. So I'm going to go 2 times 2 plus 8. 2 times 2 is 4, plus 8 is 12. 8 times 2 is 16, minus 4 is also equal to 12. So this is 12 units.
By the perpendicular bisector theorem, since SR equals 12 units, QS also equals 12 units.
Now right here, you probably were thinking, oh, well, this is 6x equals 12. I could have just used this 12. Don't assume that, because that's not true. Because if you go back to this one, when we got our x equals 7, that was not our final answer. We had to put the 7 back in for x. So you have to do substitution right there.
The converse of the perpendicular bisector theorem is also true. It states that if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So in this example right here, I have line segment MN, and I've got a point right up above it. And this theorem tells me that if the point is equidistant from my endpoints, which by the way means that the line segments I just made would be congruent, then the point is on the perpendicular bisector. So we can actually draw this situation. Perpendicular bisector will pass through the given point, and since it's a perpendicular bisector, it'll be perpendicular to line segment MN, and furthermore, its intersection point from at MN will be equidistant from points M and N, which means that these two line segments are also congruent.
Okay, let's see. So now we're right here. We just finished with instruction. So there it is, guys. I'm gonna stop recording right there. That's the lesson right there. It is a little tough. You gotta pay attention to this stuff. Now it's time to get some hard work done. New vocabulary, everything like that. So make sure you guys